I'm going to talk a little bit about oral fluid in general and how it's been used for a long time, and then how we collect samples from pigs, and then some of the published work we've done, and then that led us to the question of the stability of diagnostic targets in oral fluid. We'll talk about that, and then we'll get into some assay development stuff, looking particularly at PCR, and then PRRS antibody detection, and some new data that I haven't spoke about yet is some PCV2 data from oral fluid samples that we have. So with that, we'll get started. So what is oral fluid, and why is it a diagnostic medium? It's comprised of saliva and oral mucosal transidate and gingival curricular fluid. So saliva is obviously produced by the salivary glands in the oral cavity. Your mucosal transidate comes out of serum and across the tissues, so things from serum can find their way into the oral cavity that way. And also we have what's called gingival curricular fluid, which comes up between the teeth and the gums. That's called the curricular gap. And so between all those ways that we get things in the oral cavity, we've got our locally derived things and serum-derived things. So pathogens that are found in serum antibody can all be detected in the oral cavity, as well as the locally derived constituents, antibodies produced in the salivary glands, and etc. And also then locally replicating pathogens in the upper respiratory tract, and those things can all be found in the oral fluid. So basically, it's a really good place to look for what's going on inside of a pig or a person. I mentioned there's a large research foundation in the literature as far back as 1909. It's mentioned, and they described antibodies in saliva of humans infected with Brucella melitensis. So it's been they've been looking at it for a long time. The largest application has been in HIV surveillance and screening, obviously in humans. By 1986, they described antibody in the oral fluid. By 1994, there was an FDA-approved assay that people were allowed to use to diagnose patients with HIV. And then 10 years of assay development and improvement of technology, and now they have a 20-minute assay where point-of-care diagnostics, you go in, you contribute an oral fluid sample, and before you leave the doctor's office, you can have your results, and that has a very high level of performance. So those are very confident results generated there. This is just a brief list of human applications. We could go on and on and on about the things that it's used in human medicine, but this is just a brief list to show you kind of the breadth of it. You can detect a lot of viruses: herpes, cytomegalovirus, Epstein-Barr, mumps, measles, rubella, rotavirus, several of the hepatitis viruses, rabies, dengue, parvovirus. It's described in literature for looking for cancer. Tumor markers can be detected in it. Some of the endocrine system markers: insulin, cortisol, estradiol, progesterone. You can look at these things in oral fluid as well. So looking for drugs, therapeutic level and dose. Are you achieving the dose that you want to get a therapeutic level? And also there's detection of drug abuse. So rather than urine-based analysis for job sites and things, there's also oral fluid-based detection for drugs. And then another one is monitoring treatment progression over time, and that relates back to the therapeutic level of drugs. Whether you're looking at something going away or something coming, being present, it's an effective and non-invasive way to look at treatments over time. So now we'll kind of transition to collecting samples from swine. Just kind of some introductory remarks. It's obviously very easily collected. We know that bleeding pigs is not the case. We like to say one person, one site, 1 hour. You can collect all the samples you want. We leave the ropes in with the pigs for about 20 minutes on a good day, so it's not an involved process. It's obviously non-invasive. There's no stress on the pigs or the people compared to the alternatives out there. it's directly applicable to surveillance profiling. The fact that it's easily collected and it's a population-based sample. I like to emphasize that we can generate longitudinal data so we can look at how things behave over time as opposed to just going in and looking what we can find once upon a time. Need to emphasize it's not a replacement for post-mortem diagnostics. This is not a direct replacement of serum or anything of the sorts. It's just another tool for the toolbox that needs to be used correctly for the questions you want to answer and so forth. So don't think of it as a replacement for serum or post-mortem diagnostics. Just kind of the process of sample collection, and most of the work we've done have been in pens of finisher pigs. We're expanding that out. We'll talk about that a little later, but so what I'll be focusing here on are pens of finisher pigs. So we'll place a rope in a selected pen for 20 to 30 minutes. We like to pre-select the pens, and if we're doing longitudinal data, we want to do the same pens over time, so that's an important part. Like to hang at shoulder height to the pigs. Keeps the rope cleaner, keeps the sample cleaner. Pigs have to reach up just a little bit to get to it. That's good. Just like any livestock or any animal, routine, they like routine, so if you do it at the same time, you're going to get better response. And we like to collect first thing in the morning. Pigs seem to be more active at that point. The temperature's usually lower if it's in the summer, etc. So then after the pigs have been exposed to the rope, we'll collect the rope, extract the fluid, pour it off into a tube, label your tube, and there's your diagnostic sample. A common question we get, how many pigs do you see on a rope, or so on and so forth. There's actually animal behaviorists working on, kind of some scientific numbers, but just from what we've seen, we usually see 75% of pigs, even acute PRRS-infected pigs, you still get about at least 75% of the pigs on the rope within that 20-minute to half-hour period. This is collecting oral fluids in a commercial finisher. So if we start at the top left, like I said, we hang the rope. There's a lot of different ways that you can present ropes to pigs. We prefer not to use the rafters, but this particular system wanted to try that. I prefer to have it closer to the alleyway so the person doesn't have to go in the pen with the pigs, and obviously, we buy rope by the foot, so don't hang it from the ceiling if you don't want to buy a lot of rope. And then the pigs chew on it. I like to use a poly boot. They're tough, they're thick, they're clean, they're on site. So I'll just wring it out inside of the poly boot, and there's your oral fluid. Clip the bag, label your tube, and there's diagnostic sample out of that pen. Just some troubleshooting. Don't pool the samples. It's already a pooled sample for that particular pen. Want to emphasize collect clean as possible samples. Hang your rope a little higher so the pigs have to reach up. Sometimes if you have a pen of pigs, they're going to find the rope anyhow when you hang it, but if that first time they don't, use a little apple juice or a little sugar solution to teach them where the ropes are, and then go get a new dry rope and use that to collect your sample. They go crazy for apple juice. And then once they're trained and they've seen it before, they'll be sniffing up your leg looking for the rope every time you come, so they enjoy it. Now I'll talk about, these are two papers that we have published that were kind of laid the groundwork for this. This was an experimental study where we took different groups of different age of pigs and pens, inoculated them with PRRS, collected oral fluid and serum samples over time. We also looked at some other things. We took oral swabs for the first 3 weeks of these pigs and ran PCRs on those. We didn't have our antibody assays up and running at that point, but we did have a little IFA positive, so we had a little evidence of antibody in these samples, but what we really got out of this paper was, as we expected, so here's your serum PCR over time, and the solid line is the oral fluid for the same pigs, the same pigs in the same pen, and like as we expected, oral fluid does contain PRRS virus. It's at a little lower level. The literature suggests it is at a lower level, and we found that as well, and also a little shorter duration. So that goes along with the lower level. So under experimental conditions, we had good agreement and good reproducibility of detecting oral fluids, or excuse me, PRRS virus in oral fluids. So then we had a small proof of concept in the field. Well, this had worked under experimental conditions. Were we going to get some similar results out in the field? So we went out to three finishing barns that were known to have, PRRS circulating in them, and we collect matched oral fluid samples and serum samples from these pens. I think it was 6 pens per site, and so randomly drew blood from 5 pigs in a pen, and also took an oral fluid sample. And so this was after we'd done the experimental study. While PCV2 is kind of getting talked about a lot, so we figured we'd run some PCRs for PCV2. Turns out they're also shed in oral fluid, that virus is, so this is basically a proof of concept, and we had good agreements between serum and oral fluid. And so at this point we knew that viruses were shed in oral fluid, antibodies were in oral fluid, we could detect them. And we saw the color of the fluids, they're not a clean like a serum sample. So the question arose, are these samples stable if you collect them today, this afternoon? Are they stable by the time you get to the D lab? Can you freeze them? Some of those questions. How stable are these targets in fluid? So through a grant funded by BIV, we went out and basically collected a big old vat of oral fluid. We had 4 liters of oral fluid. I'll show you the thing here in a minute. And then we spiked this collection of oral fluid with PRRS and anti-PRRS antibody. And so the data we're going to look at here is not antibodies or virus that we're detecting in naturally infected pigs. We added these to the oral fluid so that we could then put them in different conditions and watch how they degrade over time. So there's the big vat, kind of looks like chocolate milk, and so we split it down 3 ways. One portion got no treatment, one portion received chlorhexidine digluconate at 0.01%, and the other got cathon GC at 3 parts per million. Both of these are commonly used antimicrobials. Like chlorhexidine is commonly found in mouthwash and things. Cathon is in cosmetic products, makeup, and things like that. So they're safe, effective antimicrobials. Wanted to see if they were necessary for these samples. So then we split each of these portions out into 2.5 milliliter samples, and then also in triplicate. So we took 3 measurements of each one of these samples. And then so we had all these tubes split out. You can see the little tubes they're in. So we put them at each of these temperatures. So minus 20 degrees Celsius. So this is a freezer. This is a cold refrigerator. This is a little warmer refrigerator. Now we're looking at some ambient temperatures, 68 or 20 degrees Celsius and 30 degrees Celsius. And then so over time we would remove aliquots of these samples out of the freezer and put them in a minus 80 freezer. So at 12 hours we took a set of samples out. 1 day later, 3 days, 6 days, 9 days, and 12 days later. So we put all these in the freezer, and then we randomized them and assayed them as a block. And we'll start going through these results a little bit. So there are reports in the literature that the proliferation of bacteria in diagnostic samples can break down some of our targets, and so we wanted to look at how much bacteria is in these samples and what effect does it have. So if we start at the top of the warmer temperatures, we can see that the bacteria definitely overcame both of the antimicrobials at this temperature. This was the chlorhexidine. So at time 0 it did have some of a inhibitory effect to the bacteria, but over time it did go up. Similar effect at 20 degrees, however it just took maybe a little longer for that to overcome. So here, and these temperatures are broken down statistically by non-statistical differences. So here we have minus 24 degrees and 10 degrees Celsius all basically had the same results that were not statistically different. And we can see that the chlorhexidine did have a pretty good inhibitory effect of bacterial proliferation. So that when we look at the rest of these assays, that gave us something to compare it to. So this is the effect on PRRS PCR. So again, we'll start at the top, and these are broken down again by statistical significance. But at 30 degrees, we can see that the non-preserved and the Cathon samples definitely trended towards 0 more steeply than the chlorhexidine preserved samples. So there's definitely a temperature and time and antimicrobial effect there. And then at the next lower temperature, you had a similar effect but not as pronounced. And it turns out at our refrigeration temperatures and lower, our PCRs were unchanged over time. So you can see where we're going with this. So this is the stability of our anti-PRRS antibodies over time. These would include all the isotypes, but basically it's the same story. At the higher temperatures, we see the non-preserved samples crashing early. Chlorhexidine did provide some protective effect here, a little less pronounced at 20 degrees, and again at our lower temperatures, we're not losing any diagnostic targets at those temperatures. So looks like a fairly stable sample if handled correctly. We also looked at some isotypes to see within those declining antibodies, was there a particular isotype that was more that was breaking down more than others. So at the warmer temperatures, it's the same trend, and at the cooler temperatures, and actually 20 degrees fell into this group as well, we weren't losing any of the IgA. IgG was similar. Again, the warmer groups, we lost some, and the colder groups, it was very stable. IgM is a notoriously resistant antibody anyhow, and that's what it came out in this study. So basically at any temperature, the IgM was all stable. We also looked at the pH just to see there's lots in literature about human pH, or the pH of human oral fluids. It usually tends to be closer to 6, 6.5. Looks like swine oral fluids is 8, 8.5. And with our temperature and our treatments, there weren't much differences, so it's didn't look particularly important. So the conclusions here, it looks like the PRRS RNA that's what we looked at with PCR, and the antibodies by our ELISA test, they're stable at refrigerator and freezer temperatures. So with any of our diagnostic samples, we want to chill them when we collect them, we want to collect clean, and then freeze them as soon as possible, and then they're going to maintain their integrity. And so the take-home message is always maintain the cold chain with all your diagnostic samples, but I think we definitely illustrated that here. As a side note, when we were doing this particular study, it became obvious that all PCRs are not created equal. Sometimes we think of PCR as one PCR is always the same for all different samples, and that's not necessarily the case. So the first time we ran the PCRs on that study, we had a really high rate of negative results, and we poured virus into those samples, so we knew that there was a lot of virus there. So we knew that we definitely had a problem. So we picked out a subset of 20 of those samples, and 10 that had tested positive, 10 that had tested negative, and we retested the negative ones, and some of them stayed negative. Some of the ones that were positive went to negative, and some of the negative ones went to positive. So we definitely there was something wrong for sure. And so after a lot of deliberation with a lot of our colleagues at the D lab and trying to figure out what was wrong, we decided that modifying the extraction protocol prior to the PCR reaction is very important. So then we compared 5 different PCR extraction methods on these same samples, and you can see we got very different results. And basically the point of this is, this is the one that we happened to pick at Iowa State to use. So beware of the potential problem, and definitely communicate with the diagnostic lab. Make sure it's a lab that is familiar with oral fluid samples. Also hopefully shortly we'll have a publication about what extraction protocols are good we're in the process of optimizing this in the D lab at Iowa State. So stay tuned for that information. So now we'll switch and we'll talk about antibody detection. It's obviously, we all know it's cheaper than PCRs, and we like that about it. And it's widely used in human oral fluid testing. And actually, with the HIV example, they were implementing HIV testing with antibodies before PCR was really commonly available as a diagnostic method. It was still just in its infancy and more of a research technique back then. So in the literature, most of the human research deals with antibody detection. And then a recent publication from the human literature says that most of our assays can be optimized for oral fluids. So basically, now we know that we had a lot of work to do to get these diagnostic tests up online and optimized for oral fluid, and that's where we are at the moment. But some of our preliminary work with PRRS antibody and oral fluid. So these are samples from that same experimental study where we inoculated pigs. These are the three major isotypes that we can find. This is IgM over time, and the red line is the IgA, which you might expect in oral fluid, and also the IgG, which comes up a little later, which we would expect. So we can see that we do have PRRS-specific antibody in oral fluids. So then we went to work with the IDEX ELISA, and these are those same samples. And with this first particular kit that we started using, we had excellent performance. So we have our inoculated pigs in the red line, our negative control groups down here, excellent specificity, excellent sensitivity, and we thought we were really going down the road quickly. And then the company had some problem with some materials in some of their kits, and so then these are the same samples we were using previously. We ran them on the new kit, and you can see we suffered definitely some performance. So that kind of slowed us down, but we did still know that antibodies are present in oral fluid and they're detectable. And now we needed to work on developing these assays with current technology. So we're excited about the IDEX is coming out with a new test. It's a single well PRRS ELISA assay. We're going to have our hands on it here quickly, and we have a sample set that is going to be really useful for evaluating that assay. There's been a lot of talk about Luminex lately in the veterinary research world. This is a microsphere bead assay for running ELISAs and several different assay formats, but there's a lot of research going on with that as well. SDSU, ISU, Kansas State, and Minnesota all are doing kind of different, looking at different ways to use this technology to improve our veterinary diagnostics. And it's our conclusion that antibody assays for oral fluids will be available about a year from now. They should be up and running in most of your swine diagnostic labs. So this is some new data that I haven't, like I said, I haven't talked about before. So everything had worked well for PRRS, and we're in the process of still refining our assays. And so we did some PCV2 work at Iowa State, and this was a study done by a researcher at Iowa State, and I just collected samples along with that study. So the experimental design is somewhat complicated, but it still served our purpose. So we had a group of negative control pigs that were not inoculated. We had another group of pigs that was inoculated with one PCV2 virus, as a PCV2A virus on DPI 0. The second inoculated group got the same PCV2A virus at day 0, 35 days later, and then 70 days after the initial inoculation. And the third experimental group got a PCV2A virus on day 0, a PCV2B virus on day 35, and yet another PCV2A virus out at day 70. and we collected samples out through day 98. So, and so serum and oral fluid samples were collected every other day from day 0 through 2 weeks, and then weekly out to day 98. And then we looked for PCV2 and PCV2 antibody in the oral fluid samples and serum. Going to be a lot of data coming up, so I wanted to say this first. There were no significant differences among these groups, regardless of which inoculum or which combination of viruses or how often they got it. So most of these graphs will be collapsed down into a single line for the inoculated groups. So first, we'll look at the PCV2 result, or excuse me, the PCR results, and these are the group means for oral fluid is the solid line for PCR, and in serum is the dotted line. So there weren't even statistical differences between those two samples. So basically, they're right on top of each other, and so it looks like. So here are the groups themselves, just to see what this looks like. So here are the oral fluid samples. So basically the groups all track together regardless of which of those viruses they got, and that was the same in serum as well. So this is the PCV2 ELISA. It's an in-house ELISA at Iowa State University. So we ran the serum samples, and as you might expect, 10, 12, 14 days post-exposure, we're detecting antibodies in serum. Of interest, they were still at a very high level out to day 98. This particular study actually went out to 140 days, and if this graph were to go over, they're still pretty much up at that level. These are the oral fluid samples. We're still in the process of refining this assay a little bit as well, but as you can see, negative control samples track quite nicely, and very similar to our serum samples. We're getting antibodies in oral fluid. Of interest, we've found this with PRRS as well. You start to get, you can pick up antibodies in oral fluid a little sooner than you can in serum, which is probably a product of IgM, which we saw in those isotype graphs. And so here's the IgM itself. This is serum IgM, which looks what we'd expect. And here's the oral fluid IgM. There are some spikes in the level of IgM in oral fluid, and it's present for a long duration, which is in contrast to serum. It might be in contrast to what we might imagine. So we're working on sorting this out, but it looks like it could be another useful assay format is potentially an IgM based ELISA. However, these next couple graphs I compare, these are separate assays. This is an assay meant for serum. These are assays done at the University of Minnesota, done by Mike Murtaugh, and we send a lot of samples up to him, and we've had really good results so far. So same thing here. Well, missing a graph there. This is IgG in serum, and as we expect, about 2 weeks out, we start to detect IgG, and it comes up and it stays at a high level. And the oral fluid graph looked almost exactly like it, and I'm not sure where it's gone. This is the IgA data in oral fluid. There's not a commercially available IgA assay for PCV2 in serum, and we didn't test them. We did test the oral fluid for IgA, and as we can see, there's a lot of IgA there. And again, it's present all the way out to about 100 days post-inoculation, so it looks like we're going to have good luck with detecting antibodies in oral fluid for PCV2. So some of our conclusions about PCV2 is similar to PRRS. The virus itself and the antibodies are readily detectable in oral fluid. It looks like the antibody assays are going to have excellent performance. and with these assays, we haven't finished optimizing them either, so we're hoping that they are going to work very well. There's definitely some differences among the different pathogens, the PRRS and the PCV2, so we need to keep that in mind when we interpret our results, and also we can keep that in mind when we're designing more diagnostic assays. And kind of some more broad conclusions. I didn't see the video, but oral fluids are easy to collect, and the pigs do like it. Obviously, a lot more than collecting serum. We can use PCR to detect active shedding, but we also have to keep in mind that both with serum and oral fluid, with the PCRs, we'll miss persistently infected pigs post-viremia. So just because it's a PCR negative in serum or oral fluid definitely does not mean that the pig is necessarily not harboring PRRS virus. And we know that PCRs are expensive, and we want to get away from those as much as we can to lower our cost of diagnostics. However, it's a good tool for us to have as well. And antibody assays can be used to detect passive antibody or active infection. We've got data from both of those situations. And as we saw with the PRRS specifically, IgM comes up real quick after inoculation. By day 2, 4, 6, somewhere in there, we're detecting IgM. That's that's a very cheap assay, rivaling detection time of PCR probably. And can we use that to determine re-exposures? We don't know yet. These are all things that we're still working on. So, basically our assay development is currently in progress, and there's some new technology that I mentioned, that Luminex technology, that hopefully will be coming available within the next couple years. And just talking about the antibody assays, the price is right. So if we have affordable diagnostics, we can hopefully generate a lot more information to help make our decisions. Need to thank, there's a lot of people that have been involved in this work. I've been doing it for 4 years now, and this is only a partial list. But there's a lot of industry, there's a lot of production companies, there's a lot of universities, and there's a lot of federal funding that has helped us do all this work. And I'd like to acknowledge all those people, including BIV's played a large role in it, and meetings such as this help us get the information out there. So